Hello, welcome back. This is the second part of our Desmos graph for the Collatz Conjecture video. And in this video, we're going to be looking at really using this graph, because in the last video, we looked at how to create this graph, and we looked at a very teeny tiny portion of it on how we can actually use this graph. So I'm going to make another video after this regarding how we're going to use it specifically for the music paper. But in this particular video, we're just going to look at how we can use this just generally for the Collatz Conjecture itself. And we're going to do that by initially just going through some key numbers, maybe trying some stuff out. And basically, if you didn't see the last video, we were inspired by a few of the stuff we've seen regarding movies made on Desmos using the ticker function and other Collatz graphs to create this program, which basically you can pick any number and it will apply the Collatz conjecture and show you how every number compares in the iterations. It'll also present you the number of iterations it takes to get to the 4-2-1 loop and also the highest number reached. So that's really cool. But we haven't even brushed the surface of how incredible this can actually be, because right now we're looking at 18, but this can go up to, let's for now, for this sake, say 27, right? Because that's a really interesting number that we'll go over in a bit. Anyways, 18 is a very nice number because it's got a nice display. It looks pretty even. It goes up, down, alternating until we get to the 8-4-2-1 loop. I think 16-4-2-1 loop in this case. But the thing I want to emphasize the most about this program is that we can use it to look at the Collatz conjecture, but that doesn't mean that we're going to solve the Collatz conjecture. And obviously, that's, in my opinion, not going to happen during our lifetime because we just don't have facilities for it. And it may be a possibility that it's not actually possible to solve the Collatz conjecture, and the Collatz conjecture might actually be false. But we do not have the computing power to prove that yet. The main point of this is really to have fun with the conjecture, because whilst people have wasted years trying to prove it, I don't see the harm in spending some time just actually learning it, because yes, we know it's a simple number theory question, how to prove the Collatz conjecture, but the Collatz conjecture itself is beautiful, and we'll look at how it relates to music in an even more intricate and amazing way in future videos. Anyways, so we'll start off by looking at 0. 0 isn't actually possible on the Collatz conjecture because 0 is not a positive integer. The Collatz conjecture only runs for positive integers. As we move that to 1, we can see our first dot. The way I've written this program is that when you reach 1, as in when you start the loop initially, you basically stop the program. So at 1, you don't do anything. At our point 2, we're basically going from 2 to 1. So that's what we're doing there, and it's proportionate so that 1 is halfway across this graph here. And that's how it works, isn't it? Because if it's an even number, we divide it by 2. So we move it to 3, we can see something completely different, and that's quite interesting because when we have 3, it's an odd number. So what we do is we multiply by 3 and add 1. That gives you 10. You divide it by 2, you get 5. And that's an odd number again. So you multiply by 3, add 1, you get 16, 8, 4, 2, and then we're back at 1. And it proportions it equally. What you'll notice that's different about this graph compared to the 1 and 2 is that in the 1 and 2 graph, we always had the number start at the top. And that's because when we iterate powers of 2, specifically, we always start from whatever number we're iterating and go downwards. We never go up because all that we can do with the number is divided by 2. And dividing a positive integer will always result in a smaller number. So what that leads us to believe is that when we have something like this, what we're doing is we're multiplying by 3 and adding 1, so that makes it go up, and then we're dividing by 2. Because whenever we apply the 3n plus 1, we end up with something even. So we always have to divide by 2. So whenever we have an up, we will always have a down. And that's actually the first thing that can be inferred from these graphs. Wherever you see a peak, you will always see a trough. And that's incredible because we were able to infer that just from looking at a graph. Because thinking about it two-dimensionally, if we were to think about this problem without seeing something in front of us, just that fact that we uncovered there would probably have been very difficult to visualize. And graphs are the heart of problem solving in the way that they let you see things that you wouldn't be able to envision in your own mind. And they let you uncover the secrets of so many different things. So that's what 3 looks like. When we look at 4, it's a power of 2. So again, we're starting at the top and going down. Any power of 2 will have this sort of weird slope that goes down like this. So for example, our next power of 2, 8, will also look like this. And then 16 has a similar pattern. All the numbers in between have pretty random patterns. But I think one thing you'll notice is that whenever there's a peak, there will always be a trough. And whenever there's a trough, but the trough yields an even result, we'll get another trough and another trough. And then we'll get another peak if it's odd. So that's a pretty nice way to see it. The Collatz conjecture can only be made up of a peak and some troughs, or a peak and several troughs, because it's not possible to have one peak and then another peak, which does lead us to some inference that a heuristic argument to prove this is a really big statement, and I know some people have mentioned it before, but based on this graph is what I'm saying. A heuristic argument would be, since the Collatz conjecture can't go up indefinitely on one number, due to the fact that you can only have one peak followed by troughs, we can almost definitely assume that the number will iterate below its original stance. And Terence Tao wrote a paper, a 40-page paper, where he proved this to be the case for 99.9% of numbers. I'm not sure exactly what the 0.1% of numbers were, but if he was able to prove for them as well, he would have essentially proven the Collatz conjecture. And yet, even as the best mathematician in the world, he has not been able to come up with a solution yet. And that's what I find crazy. Now, I know there's something called proving a result, but there's also finding new things. And through my Collatz paper, that's what I've been trying to do. I've been trying to find something new about the Collatz conjecture because, quite frankly, the subject has gone dry over the last few years. People are afraid to research the Collatz conjecture based on how much time they would waste, the mockery they'd get from fellow mathematicians for attempting something so ridiculous. And yes, I am trying to attempt something ridiculous. I'm not going to prove it, obviously, but I will try and find something new. And I think even by stating something that might seem obvious on second recollection, when you find something, it's always best to write it down and publish it. Because in the future, let's say 100 years from now, we have a keen young mathematician and he reads all these papers and he finds that piece of information that you found and he's like, oh, Dan, that's the last piece I needed. And that's specifically what I'm trying to do with this paper. I'm not trying to solve the conjecture because I honestly think that that's impossible. But I am trying to find something new. And that's really why I wrote this program in the first place. So let's have a look at some of the other numbers. 15 is a very nice one because initially we have a peak, trough, peak, trough, peak, trough, peak. But then we have troughs down to this number here, which I'm not sure exactly. Then we have a peak and then we have some troughs. What we can notice is that whenever we have a trough, it doesn't necessarily have to have more troughs, but it can. But when we have a peak, it can only be one peak. You can't have it can't go up and then it can't go up again. If it goes up, it has to go down the next one. So that doesn't seem useful at the moment, but it might be in the future. We've already looked at 16. 17, 18, pretty regular. We have the peaks and troughs again. And what really interests me in this particular amount of numbers is this number here, 27. And the reason 27 is so interesting is if we look at the numbers around it, so let's say 26 has 11 iterations and the maximum number reaches 40, that's less than double 26. And we have 24, and the highest number reached is itself, 24, and the number of iterations is only 11. The same applies for any number, actually, below 27. But when we get to 27, we have an amazingly large number of iterations, 112. And the highest number reached is 9,232. That is insanely high. So what I'm going to do is I'm trying to try and add another expression. So I'm going to close my two folders. I'm going to try and add another expression to basically describe these things here in terms of a proportion. So what I'm going to do is I'm going to have an expression, and it's going to be, we're going to take another point. We're going to have a label, so we're going to call it L. I'll just call it label. something highly uncreative. And we're going to have that equal, basically. What I'm thinking is we'll have the number that we've chosen, so that'll be n input. N input divided by, I think what we're going to do is we're going to have to divide it by the max number, and that's basically given by s.max. So we can just put s.max here. In this case, that's 0.002. So 27 divided by 9232, which we can try on a calculator here. 27 divided by 9232 is 0.0029, which is basically what we have here. So that works. And now we want to present that somewhere on our graph. So what we're going to do is how we created these points here. We're just going to do another one of those. And we've defined our L able, and we have what it means. So basically what we're going to do now is we're going to add a point expression. Oh, I think it'll be easier just to copy and paste one of these. And put it in here. What we're going to do is we're going to label this point. It's not being shown on the graph yet because it's orange. If we change that to white maybe, or we'll just leave it alone. We'll label it, and we'll label it in the same way we did the other ones. We're going to have to put a dollar, our curly brackets, and inside the curly brackets we're going to put our L underscore able. So you can actually see on the graph we have something appearing. It's behind that bit there, the label bit. What we're going to do is we're going to try and move that down, and we're going to do that by changing our y coordinate to probably 1, 3. That's where the other one was, so 1, 5. And a bit more, maybe 1, 9, 1, 7. 1, 9 looks good. And that's our proportion. We'll probably label this as well. And we'll label it as proportion selected number proportion. I don't actually know how to label this. Probably proportion of highest, and people can just infer from whatever they want highest number, and we'll just add that in. And so you can see that for 27 the proportion of the highest number is incredibly small, whereas if we tried something like, I don't know, possibly 16, the proportion of the highest number is basically 1, because the highest number is 16 and the number that you get the highest of is 16 as well. So that's something cool. 22 is 0.4, 20 is 1, and 25 is 0.28. So actually, something I've found here is that we can probably categorize different numbers based on their proportion, and we can put them into percentiles possibly, because 25 is 0.28, but then if we look at 27, it's 0.0029. So there must be only a few numbers. Well, I say a few, but there's infinitely many, so there could be millions. There could be infinitely many whose proportion is below or about this. So that's what we're going to look at in the next video. And then the video after that, we'll be looking at the music as well. So this is already extended way further than I thought it would, but I hope you enjoyed this video, and please like, share, subscribe. I'm trying to grow this channel. This Collatz series is just one of several I'll be doing in the future. Thank you again, and bye.